Good day, everyone. I'm Sean along with King Valencia. We are fourth-year chemical engineering student under the advisorship of Dr. Joseph Albert Mendoza. We are here to present our thesis entitled Encapsulation of Nano-Zero-Valent Iron using Ipomea batatas or sweet potato peels for the removal of copper and nickel ions from wastewater.
Good day everyone, my name is King Valencia and I will be introducing the background of our research and the problems involved that inspired our study. With the continuous rise in economic activity such as mining and industrialization processes, the environment suffers from hazards such as the increase in concentration of heavy metals in bodies of water. A study stated that the concentrations of copper and nickel in water has increased due to the manufacturing of batteries for electric vehicles. These heavy metals have long-term harmful effects to the environment and to the living organisms that will be exposed to it, which can damage their internal organs and could even cause cancer. With these problems, researchers have come up with a solution which is to use nano-size-zero-valent iron or nZVI for short as filters in wastewater. However, these particles are known to be unstable, that is why in this study, the researchers encapsulated the nanoparticles to improve their properties and performance in wastewater remediation.
The novelties relating to the nano-size zero-valent iron has increased these past years as it develops its application across environmental fields. From the term itself, zero-valent metals are those elements that contain zero-valent electrons, one of which is iron. It has the strongest reducing agent that allows for the removal of various pollutants found in water. The nano-sized iron provides a large surface area to volume ratio, which removes the pollutants faster. It is the core that provides the reducing power while the shell provides the site for chemical complex reactions. The core shell structure has an important implications on the chemical properties of nano-zero-valent iron. In spite of their effectiveness in the removal of contaminants, nano-zero-valent iron still have some weaknesses. Aggregation of bare nZVI particles decreases its surface area, which decreases the mobility and reactivity, thereby limiting the radius of its influence. Several conditions causing the nZVI particles to agglomerate includes the particle concentration, the magnetism of the particle, the size distribution, and zeta potential. There are proposed methods in enhancing and modifying the nano-zero-valent iron to reach its maximum efficiency, one of which is surface modification. Polymer integration is a section under surface modification that shows promising results in enhancing the stability of nano-zero-valent iron. Polymer intermediates such as starch, chitosan, and rice show the improvement in the stability and surface properties of nZVI and reduce the aggregation of the nanoparticles. A polymer's ability to securely anchor onto the surface of the nZVI is dependent upon its anchoring blocks. Hydroxyl groups such as in starch molecules are able to complex to iron surface and improve its steric stabilization. To be the largest producer of sweet potato peels in the world. In the Philippines, it is recorded that the annual yield of sweet potato peels is estimated to be 536,000 metric tons. It is described to be a critical staple food in the Philippines. Aside from food, it is also used for various purposes, such as starch production, food processing, and other products. With a high production rate, waste production is also high, particularly its peels. From the study of Gallo Borda, they have found that sweet potato peels contain starch, and their data shows that 7.8 grams of starch is present in every 100 grams of sweet potato peels. This implies that using the food waste product as an encapsulator for nZVI can be added as a waste management plan for this byproduct.
In this study, the researchers aim to synthesize nCVI by using sodium borohydride as a reducing agent to reduce iron. Next is to be able to enhance its physical and chemical properties through the process of encapsulation using starch extracted from sweet potato peels. Lastly, to determine the effectiveness of the synthesized material as an agent of heavy metal remediation with the improved properties of this particle enhancer. This study is limited to using starch extracted from Ipomea batata's peels as the material to encapsulate the nZVI particles. The water sample that would be used for the experimentation process would be synthetic wastewater mixed with specific doses of the target heavy metal. The study would only focus on removing or reducing the concentrations of copper and nickel from the water samples. Last are the financial limitations. Because of the limited availability of the laboratory equipment inside the campus, the researchers outsourced equipment outside the school, which is quite expensive. Moving on to the methodology.
Fresh sweet potato were purchased from a public market in Metro Manila. The fresh root crops were peeled to obtain the skin of the sweet potatoes, and the peels were soaked in double distilled water and continuous stirring for several hours until the mixture became cloudy. The cloudy solution which contained the starch was left to settle for several hours until the starch settled at the bottom of the container. The decantation process was conducted to remove the excess water, and the process was repeated until the clean white starch remained at the bottom of the container. The wet starch was left to dry for 8 hours in a convection oven at 60 degrees Celsius, and the dried starch was then collected and stored in a sealed container. For the synthesis of zero-valent iron nanoparticles, the extracted starch from the sweet potato peels were mixed with the ferric chloride solution. The solution with ferric chloride and the starch was added in dropwise to the sodium borohydride solution while continuously stirring at 400 rpm. The formation of iron nanoparticles was observed from changing of color from yellow to black, and the synthesized nZVI was filtered using Wattman No. 1 filter paper, and the filtered nZVI was dried in a convection oven for 6 hours at 60 degrees Celsius. Copper and nickel were the target pollutants to be reduced or removed from the wastewater. Synthetic solutions of copper and nickel were prepared separately. The influence of process parameters was investigated, and all batch experiments were carried out in a constant volume solution of 50 ml, contact time of 60 minutes, and stirring of 400 rpm all throughout the experiment. Different dosage concentrations, pH, initial concentration, and temperature are the parameters used and observed in the experiment. For the heavy metal determination, an ultraviolet visible spectrometer or UV was used to determine the concentrations of the heavy metal present in the sample. An aliquot of 10 ml was collected at varying time intervals and filtered using a syringe filter. The residual concentration was determined using UVs for both nickel and copper. The removal efficiency was calculated using the equation below, where C sub I represents the initial concentration and C sub t represents the concentration at time t.
Next are the research results and discussion. The scanning electron microscope was used to analyze the shape, size, and porosity of the nZVI encapsulated with sweet potato peel starch. Figure 3.1a shows the surface of the KP-nZVI coated with starch. It can also be observed from the SEM images that there are some irregularities in the shape and non-uniformity in the size of the KP-nZVI. Starch tends to provide a double positive impact. The increase in the surface charge of the nanoparticle also provided electrostatic stabilization. An FTIR was used to determine the various functional groups and chemical bonds present in the sweet potato peel starch, the bare NCVI, KPNCVI, and the KPNCVI after the batch reaction. The broadband 3322 and 1619 per centimeter in figure 3.1.2b represents the OH stretching and bending vibration caused by the adsorption of H2O on the surface of the nanoparticle. This implies that a layer of ferric oxyhydroxide was formed on the surface of the bare NCVI. The band at 616 per centimeter denotes the symmetric stretch of FeO. The encapsulation of NCVI using sweet potato peel starch added vibration bands and sharper peaks compared to bare NCVI. In figure 3.1.2c, the narrowing of bands at 3534 per centimeter indicates the possible interaction of the hydroxyl group of the sweet potato peel starch with the iron nanoparticle. Furthermore, the peak at 683 per centimeter presents improved adsorbance, implying the interaction between iron and starch during the encapsulation process. Figure 3.1.2d shows the FTIR spectra of KPNCVI after its removal reaction with nickel. There is a significant change in the peak intensities of the graph, which suggests that the nickel was absorbed in the surface layer of the KPNCVI.
The first parameter to be observed at the batch experiment is the dosage of the adsorbent. For both copper and nickel, the heavy metal removal increases as the dosage of the adsorbent increases. Beyond the optimal value or optimal dosage for both heavy metals, the efficiency of the KPNCVI stayed constant. The optimal dosage for copper is 1 gram per liter, while the optimal dosage for nickel is 0.0 gram per liter. The second parameter is the pH. At lower pH, the removal efficiency of copper increases from 54.55 to 75.28%. For nickel, at pH 3 to 7, the nickel removal efficiency of the KPNCVI was increased from 55.8 to 85.29%. Beyond the optimal pH for both heavy metal, the percentage removal of copper and nickel declined and stayed constant. The optimal pH for copper is 6, while the optimal pH for nickel is 7. The next process parameter is initial concentration. For copper, the removal efficiency of KPNCVI decreases as the initial concentration increases. The highest percentage removal for copper is 82.76% at 10 ppm. For nickel, the nickel removal efficiency also decreases as the initial concentration increases, while the highest percentage removal for the nickel attained at 82.21% with an initial concentration of 10 milligrams per liter. The last process parameter to be observed is temperature. There's an evident increase in the copper removal efficiency of KPNCVI from 82.56% to 90.32% when the temperature is increased from 26.1 to 35 degrees Celsius. The removal efficiency is 69.42% when the temperature is increased to 50 degrees Celsius. The same goes for nickel, there is an increase of 84.61% when the temperature is increased to 35 degrees Celsius. At 50 degrees Celsius, the nickel removal was decreased to 66.77%. The last part of the result is the removal efficiency of KPNCVI versus the bare nZVI for both copper and nickel. At optimal process parameters gained from the previous experiment, the nZVI with encapsulated starch has relatively higher removal efficiency for both copper and nickel than bare nZVI at similar process conditions. This implies that the starch encapsulated in the nZVI can improve the steric stabilization of nZVI, hence improving its removal efficiency of heavy metal in synthetic wastewater.
Moving on to the conclusion of the study. Again, shown in the screen are the objectives needed to be met by the researchers. The researchers were able to synthesize nZVI. This was proven through the color change that occurred wherein the ferric chloride solution turned to black upon the addition of the sodium borohydride solution. Next is that the researchers were able to enhance the properties of the nZVI through encapsulation. The SEM micrographs have shown that the particles were encapsulated successfully with the potato peel starch. The FTIR spectra has also shown the significance of the hydroxyl group present in the sweet potato peel starch. Lastly, the researchers have obtained the optimal values for each parameter tested. At these optimal conditions, the maximum removal efficiency attained was 90.32% for copper and 89.75% for nickel. Last are the recommendations for further studies.
To recap, the limitation of our study only provided the data on the copper and nickel removal performance of the synthesized nanosized zero-valent iron encapsulated with sweet potato peel starch. To improve, the researchers suggest to isolate the synthesis and encapsulation in a nitrogen-rich environment. It is also best to use colloidal grinding or laboratory ball mills to improve the particle size and shape of the nanoparticles. For further studies, future researchers can look into the absorption kinetics of KPNCVI, do a comparative study of the plant-mediated synthesis of nZVI and the plant-based encapsulation of nZVI, to use real wastewater samples, and to study the removal of lead and chromium using the same absorbent. That wraps up our thesis presentation. Thank you all for listening.